This is the last video or the last section for Unit 2. It's all about triangle relationships, specifically the exterior angle and the exterior angle theorem, perpendicular bisectors, and we go over a little bit of coordinate geometry, and we'll go over what that stuff means in a little bit here. The first video is going to go over mainly some identifications and some definitions here. The last video will have two larger examples, ones with the coordinate geometry. So we're going to get going with it right away. The exterior angle, or the definition of an exterior angle, and this goes along with your vocabulary. An exterior angle, it's the angle formed by extending one side of a polygon and using the other side from that vertex. So it doesn't have to be just with triangles. An exterior angle goes with any figure that you have, a square, a pentagon, a hexagon, or yes, including triangles. But essentially, if we were to take this point, that vertex, and here's one of the sides it was on, if we extend it just like this, and then we use the other side coming off of that vertex, this angle right here is called the exterior angle. Okay? One thing that's very special about the exterior angle, or one thing that you should know, is that it's going to be supplementary with this interior angle. So in this little example where they have written P and 120, well, we could say that that little value P has to be 60 degrees because our exterior angle is 120. They have to be supplementary, so they have to add up to 180. P has to be 60 degrees. Also, if you don't remember from before, one thing to know about triangles is the measure of the interior angles, so all the insides together, has to be 180 degrees. So a nice easy way to check and be sure that this is in fact 60 is this angle 70 plus this angle 50. That's going to be 120 plus this angle 60. Yes, that does in fact equal 180. So we can figure out the measure of that interior angle really quick using our exterior angle. Or we could figure out, again, if we didn't know this was 120, but we knew that this was 60, we could figure out this has to be 120, because again, they are going to be supplementary. So that was kind of a lot about the exterior angle. Let's talk about remote interior angles, and that would be these two pieces right here, the remote interior angles. These only go for triangles. So if you have, again, pentagon, hexagon, quadrilateral, anything else, you would not call them remote interior angles. Only with triangles, it's the two interior angles that are opposite of the exterior angle. So our exterior angle right here goes along with this guy. So we'd call this one and this one our our remote interior angles, the ones that are opposite of that exterior angle. Now you might be asking, okay, if I extend this one right here, would this angle be an exterior angle? Well, yes, it would. Again, if we know that this is 60, because it's supplementary to 120, well, then this one also has to be 120. It's the exterior angle at that spot. So yes, it would also be an exterior angle. So what is our exterior angle theorem? Well, the original theorem, when geometry was first found out by Euclid, back in the days of BC with our Greeks, he said that the exterior angle, this 120 degrees, had to be bigger than either of these ones. So it's bigger than 70 degrees, it's bigger than 50 degrees. Well, as time went along, we found out more and more about triangles, and we found out not only is it bigger than each of those pieces, the exterior angle equals the sum of the two remote interior angles. So we know for sure if this is 120, I can add these two up and they have to equal 120. 50 plus 70 is in fact 120 degrees. So that's our exterior angle theorem. So moving right along then, how can we use that to find out some of these missing pieces? Well, 92 degrees in this case, if we're trying to find our values x and y, 92 has to be supplementary with y, because it's our exterior angle with its corresponding interior angle, the interior angle that goes along with it. So if the exterior and interior angles are supplementary, we could write that as 92 plus y has to equal 180. So again, if we just subtract 92 from both sides, y has to be 88, or 88 degrees. So now that we know that y is 88, and I suppose I can write that in right here, 88 is this spot right here. Well, we know that the sum of the measures of the interior angles of a triangle have to be 180 degrees. So this 50 plus y plus x have to be 180 degrees. Well, now that I know that y right here is 88, I can say 50 plus 88 plus x equals 180. Simplify that even more. 50 plus 88 is 138 plus x equals 180. Subtract that 138 from both sides, and I would just have x equals 42. So I've solved for x and I solved for y using that exterior angle out here, 92 degrees. One more example with this. Again, we know that our exterior angle and the interior angle that it goes along with are supplementary. So in this case, this 3x minus 10 and whatever this angle is, they have to be supplementary. Okay? If they are supplementary, that means 3x minus 10 plus u, I'm going to call it angle u just because, we can call it whatever we want. 3x minus 10 plus that angle u have to equal 180 degrees. So I can solve for u then. I would just add that 10. Here we have a minus 10 or a negative 10. I could add that to both sides and get 3x plus u equals 190 degrees. And again, if I wanted to get u all alone, or just that angle, I would subtract 3x from both sides. So whatever this angle here, u is, instead I can replace it with 190 minus 3x. So we've solved for one piece of it, but we still need to solve for x in the end. Okay? So one way to do that now that we have all of our pieces is to say the sum of the measures of the interior angles of a triangle is 180 degrees. So I just plug in each of my pieces here, 25, x plus 15, and this 190 minus 3x, add them all together, and they have to equal 180. Simplifying all of those pieces, here we have a negative 3x, here we have a positive 1x, so that would become negative 2x. Here we have 25, here we have 190, here we have 15. If I add all those together, that's going to become 230. So 230 minus 2x equals 180. Solving from there, I would subtract 230 from both sides. I would have negative 2x equals negative 50. And then I'd divide both sides by that negative 2, which would leave us with x equals 25. So that was one quick way to solve it. X equals 25 in that case. Another fast way to solve it is, remember our theorem said that this one had to equal these two added up. So we could say 3x minus 10 equals 25 plus x plus 15. Working from there, this 25 and this 15 added up become 40 plus x is left on that side. This side is just 3x minus 10. Continue going from there. I could add 10 to both sides, and I could subtract x from both sides. If I do that, that's going to leave me with 2x equals 50. again, I just divide by 2. I get x equals 25. So 2 different ways to go about it. Again, you can set them exactly equal to each other, like the second round, or you can figure out one piece at a time and work your way through it. Either way, we figure out that x has to equal 25. The perpendicular bisector theorem. Before we talked about what a perpendicular bisector is, if we have any segment, so here I have a line, or should I say a line segment, it goes from A to B. A bisector is going to cut it exactly in half, so it has to go through its midpoint. A perpendicular bisector not only cuts it in half, but it cuts it in half perpendicularly, so straight up and down. So we'll say that's our perpendicular bisector. That means this length from here to here has to be the same as this length from here to here. Okay? And cut it at a perpendicular or 90-degree angle, so that's our perpendicular bisector. Now the theorem says if a point is on that bisector, then it's equidistant from the endpoints, and it's now bisects the angle. And it might be kind of confusing. What that means is if I have this spot right here, we'll call it C. Okay? It's equidistant from A and B. So what that means is, because C is on this line, the perpendicular bisector, A to C equals C to B. AC equals CB. Okay, because C is on that perpendicular bisector, it has to be just as far in both sides, or in both cases. Let me get rid of these. Give myself a little more room to work with. Let's try another one in green. Down here, call this one D. Again, because D is on this perpendicular bisector, D to B is exactly the same as D to A. DB equals DA. We know that for sure because it's the perpendicular bisector, because this length is the same as this length, and because this is a 90-degree angle. So it has to be. Another thing that it tells us, again, when it says bisects the angle that's made at this point, so if I put, again, C is right here, this angle has to be just as big as this angle. It has to be. Because C is on the perpendicular bisector, that angle that it creates there has to be just as big as the other one. Similarly, this angle has to be just as big as this angle. Again, it has to. Kind of just part of the definition. If we look at where D is at right here, this angle is just as big as this one, and this angle is just as big as this one. It's just part of the definition of the perpendicular bisector, and more so, it's the definition of a point that lies on the perpendicular bisector. We're going to go over just a few more definitions here. Definition of a coordinate proof. This is looking at coordinate geometry. A coordinate proof is a proof that uses the coordinate plane. So again, we're going to look at our XY coordinates, plot some points, and use some of the things we know about proving things, specifically using that coordinate grid. Okay, so a lot of times this will use slope, the midpoint formula that we learned from before, and the distance formula. Okay, this one is probably not in your notes, but I want you to write this down at some point if you've forgotten this one. Given 2 points, x1, y1, and x2, y2. So again, this is kind of just, it starts just like our midpoint or distance formula. If we have those 2 different points, one here and one here, the slope between these 2 points, so going from the first point to the second point, slope, we use the variable m. We'd say m equals y2 minus y1 over x2 minus x1. You probably remember that from when we were using things like y equals mx plus b, so finding linear equations, and we want to define the slope, well, we can still find the slope using just our 2 points. Okay, and that slope is going to be important. Part of why it's important is if we look at parallel lines, the slope of any parallel lines. If I have my coordinate grid right here, and I have one line here, and this one is parallel to it, they're right next to each other in parallel, the slopes are equal. Okay, the slope of the top line is the same as the slope of the bottom one. So we'd say m equals m in that case, or slope equals slope. It's the same exact number. Slope of perpendicular lines, so in that case, if I had my coordinate grid, and I have one going like this, and another one cutting it at a 90-degree angle, just like that, perpendicular lines have slopes that are opposite reciprocal. So one way to say that is m equals negative 1 over m. Okay, that negative part is the opposite. Reciprocal means you flip it around. So if these were perpendicular lines and one of them had a slope of 2/3, well, the other one would have to have a slope of negative, because it's the opposite, so positive becomes negative, negative becomes positive. You'd say negative, and then you flip around the fraction, 3/2. If these are the slopes of two lines, we know for sure that they are perpendicular, because they have opposite reciprocal slopes. On our last pieces of review here, the distance formula, as you could probably remember from before, d equals the square root of, so underneath, everything is underneath this square root, x2 minus x1 squared plus the amount y2 minus y1 squared. Okay, that distance formula comes from our Pythagorean theorem. The midpoint, again, if we have those two different points, we figured out we can find slope between them, we figured out we can find the distance between them. The midpoint, so the exact middle between those points, is x2 plus x1 over 2, so we're finding the average x value, and that's going to be our new x coordinate as we find the average of the other ones, and y2 plus y1 over 2. So again, the average of that's going to be our new y coordinate. Now again, you don't just want to write these as two numbers, x and y. This is a coordinate that goes on the grid somewhere, so maybe it goes right there. So you need to make sure that you're writing the parentheses and the comma between them. So we know that it's a point on the grid somewhere. That would be our midpoint then. Oh, I'm not going to go over this example in this video. You can watch it in the next one.